This video file was recorded in Sabunji University during recitations for the CS204 Advanced Programming course as it was given in the spring semester of 2017.
Hello guys. Today's topics are going to be threads and mutexes. They're important topics. We have been using threads, we have been using mutexes, but we didn't know how to use them. What were they actually? So, let me start from beginning. Very often, usually, you want to run multiple programs in your computer. Like, you want to do your homework, your assignments for CS204. You want to watch a movie, you want to play a game, you want to write a Word document, and so on. For each of those programs, usually a program is running, and that program that is running, that is being executed right now, it's called the process. Let me write processes like one. So this is process one. Let's say this is Visual Studio or program. You can approximate process to program right now. We won't go to details. This is your game you're playing. This is P3. Let's say this is your Word, or this is your Word document you're writing. This is your game. You can use many other programs. You think that you're running all of them in parallel, but actually it's not the case. If you want to run, let's say, 10 programs at a time, you should have 10 processors. But you have only one. So what is happening is the following. First P1 runs, afterwards P2 runs, then P3. Again, P1, P2, P3. And this is called pseudo-parallelism. Okay? They take turns. So let's say like 10 milliseconds is given to this guy, then 7 milliseconds to this guy, then 15 to this one, and so on. I'm making up the numbers. They can be of the same time, or the same quanta. But our senses are not sensitive enough to feel that they are running in parallel. Of course, if you run like 10 or 15 programs, then you'll see that like your program is stuck, and you can feel that something is going in the background, okay? If you run like 3 games or 2 videos at the same time, plus 2 Visual Studio processes and so on, you see that it's getting slower. The reason is this one, that the quantum time, the time that each process is given from the processor, is becoming less and less, so our senses now can feel that something is going on the computer. So this is what a process is, a program that is running. Usually those guys compete for the processor. Each of those guys want to get as much time as it can from the processor, because it wants to finish as soon as possible. However, let's assume that here we have a Word document, Microsoft Word, a word processing tool. It might be Microsoft Word or OpenOffice. If you have used Linux, for sure you have seen OpenOffice. OpenOffice Word is the compatible or the alternative in Linux of Microsoft Word. So let's say we here have pages, 600 pages, I'm making up the number. And you're writing. As soon as you're writing, what you have entered to the keyboard, you see here. Okay? But sometimes you might delete a paragraph, let's say at the second page. And when you delete something at the second page, maybe the page that was, maybe now you have not 600 pages, but because you deleted a paragraph at the second page, now you should have 599 pages. That means that all the paragraphs should go to a new page, to the previous page. And it's a lot of processing. That's why what happens? So this is our Microsoft Word document, and inside it we have something we call a thread. It's a lightweight process sometimes, this is how it's called. We have multiple threads that are doing the same program, are working on the same issue, let's say in our Microsoft Word. So this thread is waiting for us to give something from the keyboard. And as soon as we give it, it prints it here. We have another thread, let's say this one. Well, this thread also works on this guy. And this thread, whenever we delete something, whenever we add something, it's doing some mad processing on the background, like arranging pages. So instead of having 600 pages, what if we delete one page? It's going to delete, and the deleted page is the first or the second one. It's going, all of the pages is going to shift them by 1. Okay? So the 600 is going to be 599 and so on. Okay? That's why when you do some nasty stuff, when you do some when you give a lot of job to your processes, sometimes you give multiple characters as an input, but they don't appear immediately. Why? Because this thread that is doing some background processing that you don't see has taken the turn, and it's processing. When this guy is issued, that is waiting your input, it will give the whole input immediately. Okay, so this is one of the reasons. Of course, we can have another thread. Like, for instance, you might have grammar checking. If you do some grammar mistake, syntax mistake, in English language, you'll see it will be underlined with red. Okay, so this is another thread. What I wanted to say, that those are different processes, and inside of a process we have a kind of a function that we call thread, and it's doing some job. Those threads can all of those can see everything inside. They share this document. Okay, everything which is included to this P2 process are sharing those guys. But process 1, if you're playing a game, any game, can the game see the document here? What do you think? Yes or no? No, because it's not associated to the game. Because otherwise it would have been a virus if it can change anything here. It can see only the portion of the RAM memory or the hard disk that is related to this game. Okay, that's why those compete to each other. They see each other as an enemy because this guy is trying to take processing power from this guy. Okay? But threads are friends because they're working towards a common goal. So this is a process, this is a thread. Usually we have tens, dozens, 60, 70, 80 processes running simultaneously in our computer, but we have hundreds, maybe thousands of threads because each of the processes have multiple threads or at least one thread. Okay, it can have multiple threads, but it should have at least one thread. Now let me show you something at my computer currently. It's not overloaded. Let's go to the task manager. And here we have the number of processes running, namely it's 66 right now, and the number of threads, it's 945. Okay? Some of those 940 something threads are related, actually all the threads are related to one of those 64 processes. Of course, only Visual Studio is a process that I generated. Others are related to networking, to something that operating systems must have. Okay, if I open a new file, if I run a new program, you will see that the number of processes are going to be increased. Okay, so let's go with the first program. But before doing that, so we saw what a thread is. Now let's see how can we generate threads, how we create them, and so on. In order to do that, we have a class. And the name of the class is, you can guess it, thread. Okay. They have private variables, public ones. So I'm going to show you some public methods, functions, which are the most important. Of course, it's a large class. But since we are beginner in terms of threads, I'm going to show you the most important ones. So, the first one is the constructor. You call it by giving the name of the variable. Let's say, it's a thread. Let's say the name of the variable is my thread. And here here we have the parameters. The first parameter is always the function that the thread is going to run. But it's given not as a name, as a parameter. So the name of the function now is given as a parameter. Okay, let's assume that this function has its own parameters. That's why we are going to have the parameters here. So this is parameter 1, parameter 2, and so on, up until parameter n. Those parameters are the parameters that the function takes. Let's say we have here the function, which is doing something, and here we have the parameters of those functions. Namely, if you're waiting for an input, then you can assign a function to this thread, which is a while loop. While C out and C in, you're taking something, then print it here. Okay, something like that. For instance, So this is the constructor. This is how it works. Now when you create a thread, always when you start, let's say we started with the main program, with the main function, always we start with that, we have the main thread. Let's say this is the main thread. If you create a new thread, it's created but it's not doing anything. And usually the thread that is created, so if this is created for main, this is the first thread, we didn't have them. When I created this thread, main is the father of this thread. And usually the thread that is created is joined to this one, meaning it's joined to this process. They work in the same process, they can see the same data. That's why we have the function join. So the thread can join the group of other threads that are working towards the same goal. Let's say it's word processing stuff or whatever. So this is the function join. In order to join it, we should ask whether it's joinable, usually. If you are sure that it's joinable, we do it. Otherwise, you don't join it. How do we know that it's not joinable? If we didn't, because sometimes the programs might be long. Let's say we just created this thread, we joined it here. But later on, we want to join this thread to another process or somewhere else. If it's already joined, you cannot rejoin it again. That's why you should ask whether it's joinable or not. It's like you are working in a company, and that company have a lot of workers, and if a worker works for a certain company, you cannot hire him. Okay? So if the thread is already joined to a process, you cannot join it again. Okay? But if you try to join it, something that is already joined before, the program will crash. That's why you should ask first whether it's joinable. So this returns true or false, meaning I want to hire someone, but I have to ask whether he's already hired. If he's hired, I cannot hire him. Otherwise, I'm hiring it. Detach. This is another function. Usually, when I create threads, they're working towards the same goal, and they join towards the same process. But sometimes a thread can be independent. So this guy can work something different. Okay? In order to work something different, we detach him. Okay? Usually this is not a good way of doing things. I don't prefer it. I've never used it, but it exists. Because if I do something, if I open a company, if I take workers, I want the workers to work for my company, not for something else. Okay? But if I'm a humanitarian guy, I can say, okay, I'll pay you, but you work for someone else. Which doesn't happen usually. Yield. Now, those processes compete with each other. The processes P1, P2, P3. They want to grab as much time as they can from the processor. Of course, we don't ask them how much they want, or usually the operating system schedules them. Let's say it says you're running for 5 milliseconds, you're running for 10, you're running for 7 milliseconds, and so on. It goes in a way in a cycle. But threads inside the process, they should cooperate. And sometimes when I say, okay, it's your time to work, and you have, like, let's say 7 milliseconds to work, this process might say, okay, I'm going to give to this main thread 2 milliseconds, to this one 2 milliseconds, and 3 milliseconds to this one. Okay, it's like I'm having a company and I have a budget, and I should spread the budget among the workers, but they're not equal. Okay, and someone have the IELTS degree, someone not. So this would be the analogy here. Okay, but some of the workers might say, okay, I have money, I don't need that really. I want to take a vacation, holidays this month. That way, don't pay me anything, but I'll have a holiday. You call this is yield, meaning that although I have 3 milliseconds to use, I'm giving it to others. This works usually inside the threads of a process. What else do we have? Sleep until. Okay, you might say to your workers, okay, until the 10th of May, you can have holiday, you are not going to do anything, but afterwards you're going to work twice the time. Okay, so this is sleep until. When you need the threads to start working at a certain point of time, let's say 12 a.m. today, we start working together. Another function similar to sleep until is sleep for. Instead of saying sleep until Sunday, it might say, okay, sleep for 1 day. Starting from now. You have holiday of 1 day. Okay? So this is all you need about threads.
Does it compensate for the sleep after?
Depends on the function that it's calling, and depends how things are arranged inside the process. Okay, maybe I went through some details because this is actually operating system stuff. But in order to understand today's topics and today's codes, I think you should know at least this stuff. Now let's go and see an example with threads. Now you might see why we need multiple processes, not only because you want to write, you want to execute multiple programs at a time, because you want to play a game and write your assignments and write on Word. But sometimes you're running a program and you're thinking about the input. It asks you like, okay, give your age, and you're thinking, okay, my birthday was last week, so am I now 28 or 29 or something like that? So like 30 seconds might pass before you give your input. 20-30 seconds are a lot in terms of processing power. So while you're thinking about the input, your thread that is taking in your input, is waiting for your input, the operating system might say, okay, this guy or this girl, let him think, I'm going to run other programs. So in this manner we are utilizing the processor, so it's constantly working. And if you see the processor is constantly working here, you see the performance is here, and now it should be utilized always. Now let's go and see the first program here. It will be better not to download. I mean, you can do the same. I'm going to close this stuff, or maybe I'll need it later. Okay, so this is my guy. I'm pasting it here. Okay. So, the first example for today will be independent threads. Let me enlarge the font. Let me show the task manager again and the. So we have here 66 processes and 985 threads. Okay, so I'm running the program now, and you see the number immediately increased to 70 something when the number of threads increased, because I'm running a process now which has some threads inside. We created not only one. Main is one thread, usually. Not usually. In this case, we're going to add more threads. That's why the number of threads increased here, and the number of processes as well. So the output, we didn't see that. Let me see it. So system, pause. Okay, this is my output. And you see I have here 72 processes and 1053 threads. So basically what we are doing is simple stuff. Beside the main thread, we have two other threads, thread 1 and thread 2. And they take turns. You cannot figure out who is going to take the turn. It's 1, 2, 1, 2, 1, 2, but sometimes it can be 1, 1, 1, 2, 2, 1, and so on. You can never know that. And we are just printing, okay? The thread 1 and all of the threads have ID. And by the way, I forgot to tell you the ID. Not only threads, the processes also have ID. So another function here that we need is get ID. All threads have unique ID, and with this get ID, we take the ID of the threads. And this is our output. Now let's see how did we get that. And let's see the problems that are going to occur. You see, when I close that stuff, the number of processes and threads decreased immediately. Although here we are going to create 3 threads, but there are some other background threads and processes going on that we don't see them. Okay, what we have here is the following. We have a function. It takes an ID as an integer, which is ID, and we iterate from 0 to maximum, and see maximum is a global variable. In this case, it's 7. And what we do, we create an O-string stream called output. And here we print this stuff. So thread ID, this is the ID that we send. and afterwards thread ID that the system, the operating system sees it, and we can get it by this thread get ID. Okay, is blah blah blah. Okay. So, and of course, this is attached to the output, and finally the output is the content of the output is converted to a string, and it's given to cout in order to see it in our screen. So what we are doing here is the following. Let's say this is not the word processor anymore. This is our output. And here, this is our program that we are running. This is the main thread, again. And now we create two threads. But those threads have their local variables. The local variables in our cases, so each thread is going to run this function twice. It might be different functions, but in this case, it's the same function. It's running that function. And you see all of the threads, any of the threads that is running this one has an output of O-string stream. So this is, I'm going to write it O-string stream, O-string stream. This is related to this guy. This is related to this guy here. And they're running. They're different variables. Okay, because we call the function twice. How do we do that? Well, very trivial manner. So this is main. In main we declare, I forgot to tell you, in order to use threads, you should include the thread class. It's done like this. Include the thread library, actually, which has a thread class inside. So we create a new thread called thread1. As the first parameter is the function that it's going to use, and this is the function, function1. If it was function 2, it would have been function 2. Function 1 expects an integer as a parameter. That's why we send 1. This is the ID. We create another thread, function 1. Again, it calls the same function. It expects a parameter, ID, of integer type. So this will be our ID. We join both of them. When we join them, they can start processing, working. And when we join them, they start executing this function. Both of them are executing the same function, but different instances of the same function. Okay? You know what instances is, okay? So this is the function. When I call it with parameter 1, I've created one instance that is being executed. When I call it with parameter 2 for the ID, I'm creating another instance of the same function. And it's being executed, and we saw the output. So far, so good. We can create two functions. Usually it's not the case. Usually one thread is working on one function, another thread is working on another function. As I told you, one thread is waiting for our input for the word processor, so we can print it. Another thread is doing some background stuff. Another one might check our grammar mistakes, and so on. But let's change our code slightly. Let me give you the output again. So this is the output. I'm printing the IDs here are 1 or 2, but the IDs that the operating system sees are given with get ID. Now instead of using O-string stream, let me do something like this. I'm using cout. I'm directly printing them. Why should I complicate my life, you might say? So I'm running the code. You see what I'm getting? Something which is not expected. Okay? This is not what I'm expecting. So I started with thread, and I should give the thread ID, but at that point of time I stopped. Because the operating system said, okay, it's enough. You should work with the other guy. Then I start with, probably this is thread 1. So I start with thread 2. I print the ID of thread 2. It's working with I is equal to 0, and I'm finished. Then, you know, thread 1, comma, thread ID. So this is what I'm trying to print. Thread ID, comma, thread ID, this ID, is working with which iteration? It's working with I is equal to, and I is this one, from 0 to maximum, to 6 actually, maximum minus 1. But in a way, this thread was stopped, and the other one took the turn, and somehow we have this garbled output. Okay? It's more obvious if we increase it. Let's say we have 100 iterations. So this is what we get. Yeah, sometimes it's okay, but sometimes it's garbled. So what is the problem here? Why we introduced threads? We saw it because we need multiple threads to work on the same goal. But what's the problem here? Can you tell me? I'm giving you a hint. How does cout work? Cout works that there is a buffer inside the cout. We append the data that we want to print, and whenever we see semicolon, it's going to be printed. And you might say, okay, why we didn't get the same mistake when we're working with O string stream? And why we're getting this mistake when working with cout? Hint, another hint. You see O string stream is a local variable to this thread. O string stream is another local variable to the other. They're different. What about cout? Cout is actually a global class that is shared among all of the programs. It's like declaring it here. You see, the maximum can be seen by anyone, so cout is also here, like a global function. It's actually a class, but let's assume it's a function that has a buffer, and everyone puts whatever he wants there. Whenever I see semicolon, I'm printing the buffer, and I'm clearing it. I'm flushing the content, okay? So what really happens is the following. Now, I don't have those O string streams. What I have is this cout guy, and this cout guy has a buffer, and both this thread and this thread share the same variable. Okay? So when this guy wants to print something, like let's say thread 1, blah, 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 but it didn't finish till the end. It didn't reach semicolon. And the operating system says, okay, it's enough. Now it's your turn of your friend. So this thread starts to append its content. And it goes thread 2, blah, blah, blah. When it reaches semicolon, it is showed here. But it showed something like this, in a garbled fashion. Okay? So, is this clear or not? Yes or no? Do you have questions about this stuff? How many of you understood it? Raise your hand. If you have questions, ask. You? Okay, maybe later. Okay, if I have semicolon, everything is printed. Part of the input might be from one thread, from another thread. If we have multiple threads of other threads as well, it will be more complicated. Now, how are you going to solve this issue? Not only this one. We might have other problems as well. Like what? Here we have printers all around the campus, like 20 or 30 or whatever. In each floor there are printers. But if you have seen, the queue of the files that we want to print is common for all of them. So in a sense, we have something like this. It's not infinite. You might assume it's infinite, but there are slots, maybe 100, 200 slots for printing. And they are named. Like, let's say this is slot 0, slot 1, and we have the files that we should print. Slot 1, slot 2. Slot 3, let's say it's empty. Of course, 4, 5, and others are empty. Now, what we have is the following. We have a process, or a thread, let's say, that it first, this is how they work. So let's say this is thread 1. Checks emptiness, whether this is empty, whether I can put a file there. Increments counter, CTR, puts file, or better, we might say that first it puts file to be printed and increments the counter. Exactly the same thing is done by another thread. So it checks emptiness, puts file, and increments the counter. the counter for the time being is at 3, meaning this is empty. So, let's say we have 2 threads. You might have hundreds of threads. This guy wants to print something, and this guy has created a thread, maybe a process, and it wants to put his files here. So he starts, and he says, okay, check whether this is empty. Yes, this is empty. So this is done. Then he puts his file there. So this guy puts his file here. Just about when he wants to increment the CTR, and he knows that the CTR is 3, so CTR here is 3, the counter, he stops here. And the operating system says, okay, enough. Now it's the turn of your friend. So this guy now starts, also checks emptiness, and he says, okay, it's empty. This is done. He puts his file there, but when he puts his file there, this guy is erased, and he puts his file there. Okay? This is done. He increments the counter. The counter is incremented. I might say that puts the counter here, so the counter is going to be 4 here. Okay? Now the operating system says, okay, enough of thread 2. Let's go with thread 1. And thread 1 starts. And where did it left? It left here to increment the counter and to put it. But remember, the counter was 3 for this guy. So this guy, again, erases this counter, but it doesn't matter. Counter is 3, meaning the 4th slot is now empty. But hey, do we have a problem here? This guy is waiting for his files to be printed, but they're nowhere to be seen. He's waiting in vain, because this guy, thread 2, overwrote his files, deleted them, and instead put his files. Do you get this stuff? Okay? So this is a problem. This is one problem that we saw with the cout. Another problem is this one. When 2 threads should work in the same region, it's called the critical region. The critical region is the shared region, this one. And what we need is called mutual exclusion. Meaning, when one thread is working here, another shouldn't work. But when it's working, it should finish all of this job. So the other one should start. So how would you do that?
Lock threads.
Lock what?
Lock the threads until the other person.
Exactly. Your friend is correct. So what your friend is saying is the following. So this is my 3rd slot. And it says the following. When this thread starts executing its file, I'm putting here a lock, something like this. A key, let's say. Meaning that right now I'm working here. I put the lock here when I start. And I release the lock when I finish here. That means I start, I check the emptiness, it's empty. I put the file, so I put the file here, 3. Increment the counter now is going to be 4. Release the lock, and I'm releasing the lock. Even if the operating system says, okay, stop, it's the turn of this guy, when this guy tries to access this part here, it won't be able to do so because of the lock. Because of that key, because we've locked it. Now, so it will stay okay and will say, okay, I'm sorry, I cannot do something because it's locked. Again, this guy will be rescheduled. It will finish, we'll put the lock, we'll increment the counter. Now thread 2 will start to execute itself. So check the emptiness for 4, put the files here, increment the locker, the counter to be 5, meaning this is the next empty slot, and this is how it works. So the key here is this lock, the key, meaning that exactly, that's why we have another class which is called MUTEXes. So let me erase the board. We don't need this stuff anymore. These are called MUTEXes. MUTEXes come from mutual exclusion. Mutual exclusion means that only one can work in a critical region. Mutual exclusion, MUTEX. In order to do that, you should include the library of MUTEXes. Include MUTEX. And inside we have the class MUTEX. And I'm going to tell you only the public, two of the most important public functions, which are lock and what? Unlock. Lock, when I put the lock, no one can enter there up until I'm finished and unlock it. Unlock, so others can go inside. Now let's see how it works in our case here. Okay. Let me run the code again. The problem with the printing stuff, so this is called a spooling directory, when you have a queue for files to be printed, is the same with the cout. Namely, when this thread wants to print something, the other thread shouldn't be allowed to print anything else, to put anything else in this buffer up until I put semicolon. Okay? Because otherwise the output will be garbled. We don't know. I mean, it's something that you don't expect. So when this thread is trying to print something again, we should let that thread to work in this buffer, which is a kind of shared with not only the threads, all of the processes here, up until I put semicolon here. When I put semicolon here, then I'm releasing the lock. So let's do it together. First, I should include the MUTEX library. Include MUTEX. And I should declare a MUTEX. MUTEX, I'm calling it my MUTEX. This is the name of the MUTEX. Now, where should I put it? When one thread has entered this region, I should lock it, but where? Just before entering. And when should I release it? Just before I'm finished. Okay. So the garbled output is this one, as you can see it. But when I do this stuff here, my MUTEX lock, no one can enter and print anything else, but only this thread that has locked the MUTEX, my MUTEX.unlock. Now let me run the code. You see, I don't have the garbled output. Everything is perfect. Okay? So this is how it works. Besides the MUTEXs, you have other ways to do things like locking and unlocking, but the most preferred and the most easiest you can use are the MUTEX. Okay? Any question? So this was a good example to see how threads work and what were the problems that we were dealing with when we introduced the threads, namely when we have to share same region. And we had the solution for that, which were, in our case, MUTEXs. There are other solutions, like monitors and TSL locks, which are assembly language, but you don't have to go through that. If you don't have any question, I'll give you like 2 or 3 minutes of pause, not more, and we go with other examples. We have 4 to cover today, but this should be enough, because I know we covered threads and MUTEXs, and these are the new topics for today. And in the rest of our time, we are going to see examples with those. I think you need like 2 or 3 more minutes to digest this, so we'll be back.